In this session, we will solve the fourth example of a STI, Schrödinger time-independent equation, and each time gets a little bit tougher. And so this will be the last example of this chapter, of chapter 2, and chapter 3 will be on. It's a short chapter. It's just basically to introduce a mathematical concept that's very useful in quantum mechanics that we will use from now on, called the delta function, D-E-L-T-A, invented I think by Dirac. That's Paul Dirac, the British theoretical physicist, the famous Dirac of Dirac equation, the relativistic quantum mechanical equation that if you keep following me, we will do in M1 level, first year master's level. So, right, but for this one, it's this fourth example is on a bouncing ball. So it's so you imagine your x-axis. So it's still one-dimensional, but you imagine now that your x-axis now is vertical. Okay? So the ball is just sort of bouncing, boing, 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 boing. And it's in a potential. The potential this time is gravitational, so it's a gravitational potential. And the form it takes is of mgh. Well, h is the height. Like if the ball is, say, here, for example, and it's been lifted up this distance, h. So it'll have a potential mgh. That's just from classical mechanics, right? But h in this sense is just x, right? So when you plug in your potential into your STI, Schrödinger time-independent equation, you'll get this. Well, here, okay, and here's your potential term. Here's your v, right? We put x instead of h because our x now is this vertical direction. Now the potential, there's no mention of t in it, right? So it's a time-independent potential. And that means that the wave functions, your u, will be, what's the word? I'm trying to think of the technical. When the potential... Right. Okay, so here's your STI. Okay, here. Now, it's still a little bit complicated. You can simplify it, and there are various tricks in solving differential equations to simplify things. Now in this case, you make a linear transformation. So you introduce a new variable, instead of it being x, you introduce a new variable z, and x and z are linearly dependent on each other, so x depends linearly on z, right? Now I'll ask you to do this for homework, to substitute, where you have x here, put this form, a z plus b. A is just a constant. If a cubed, if you allow a cubed to be h bar squared over 2m squared of g, you say, where did that come from? Well, this is your homework. So choose x to be of this linear form, and if you get these conditions that a cubed equals blah blah and b equals e over mg. So now a is a constant because these values here, h bar and m and g, they're all constants. So a cubed hence a will be a constant. But b here depends on the energy. Right? It's E defined as E over mg. Right? Now if you let x be az plus b, then recalculate d squared u by dx squared and get it in the form of d squared u dz squared. So you need to find out what this is in terms of this. So do it as homework, and you'll eventually get that if a cubed takes this form and b takes that form, then what you got on the right hand side becomes zero. It cancels out, which is nice. So you get this sort of very convenient form. So you can rewrite, translate this, the usual st into this much simpler form? Well, yes and no. I mean, you do have this z variable here. Okay, so the actual equation is more complicated than what we're used to. Now, it's at this point where you start hesitating. Are we solving differential equations, or are we doing physics? Right? So it starts becoming fuzzy at this region, because starting to solve an equation like this, you need to be pretty much a specialist in differential equations, because this type of equation is a particular form of a Bessel equation. Now, I won't go into it. Studying Bessel functions, Bessel equations is a whole specialty. You can do chapters on it in textbooks on differential equations, DEs. So I'll sort of compromise and give you a bit of a hand-wavy feel for what's going on. I won't actually give the explicit form for you, the solution to this equation. But it's called a Bessel equation, and for those of you who do know about such things, just off the top of my head, it's of order a third. So if you don't know what I'm talking about, don't worry. Just remember that this function u here is a Bessel function. It's a particular kind of function that solves differential equations like this. All right. Now, if you have a Bessel function of order third, it's fairly common. So it has its own name, and they're called airy, A-I-R-Y, airy functions. Right? And there are two forms of these airy functions. There's the A form and the B form. Now, we can bring in some physics, and we can reject the B form solution for u here, because the B form cannot be normalized. It just blows up. Right? So you reject the B form. So that just leaves you with this A form. Now, there's a particular formula for this, and it involves integrals and cosine and t cubes, and don't worry about it. Right? If you're interested and you want to find out about airy functions, we'll go, Google it, or look it up in a math book or something in differential equations. All right. So this the A form of the airy function, whatever it is, your wave function here, u, is proportional to it, right? So it's a of z. This is a solution to this equation, right? And this equation you got from your bouncing ball potential type problem. All right. Well, z is just x minus b divided by a from here. Okay. Now we can apply some of the constraints on the wave function, like continuity, like the potential here effectively, it's impenetrable, that's the ground, if you like. As a bouncing ball, the ball does not go into the ground. So effectively, the potential here, say, is infinite, right? So therefore u here is 0. And so when x is this distance, one-dimensional, but vertical this time. When x is 0, your u has to be 0 by continuity, because the u here is 0. So the u here, well, infinitely close, also has to be 0. Okay, so u has to be 0 at x equals 0. So this x disappears, and so you will get u, which is this. So u is 0. So in other words, when x is 0, this airy, the A form of the airy, the x is 0. So just get minus b over a is 0. Okay. Now there's an actual formula for this airy function. It's quite complicated, but so when the variable in that function, if you put minus b over a into that, and then solve this equation so that the a form equals 0, that will give you values for minus b over a, right? And if you know a, now a is just a constant, but b, so if you can find values, solutions, minus b over a for this equation, so that means you know what b over a are, gives you this a form equaling 0. But b, you see here, depends on the energy. So if you can solve this equation, you'll get values for minus b over a that give you ai, or the area function, equaling 0. And so you know what minus b over a are. They're the solutions to this. And since b involves e, that means you can, from these solutions, you can find what the allowed energies are. Okay, so we've done this kind of sort of thing before, right? Now, I've drawn a graph here of what an area function looks like. So a of minus b over a, and b over, this axis here is just b over a, and it's a kind of oscillatory motion, but it's sort of dampening. It's sort of going down as your b over a increases. Now, these intersection points here with this axis, in other words, when a minus b over a is 0, right? So here, and so on. So you get an infinite number of them. These points here, the values of b over a give you the area function equaling 0, and from these b over a values, so what's this one? 2 point something, I guess. This one's I don't know, around 4. This is 5.5 or whatever, 6.5. These values. So so you get these numerical values for b over a, and that allows you to find out what E is, what the energy is. Okay, right? And you'll get an infinite number of them, but discrete energies, quantized energies again. Our usual story. Right? Okay, so you now know what these discrete values of E are. So now A is just a constant, but if you know your E, you know what the B is. So you know the numerical value for the B and A as well. Well, now since the wave function U here is proportional to the area function, we have not normalized it, but anyway, A is proportional to the area function, and the area function of z, but z is x minus b over a. Now we know A and B, because if you know the energies, you know what B is, you know what A is, so you know what these two are. So you can actually plot now. You have to do it with a computer, but the wave function u here, which is proportional to this, you know A and B, so you can actually plot the area function. In other words, plot the wave function for your u. Now if you do that for say the first 3 energies, 1, 2, 3, you get, they sort of look like this, right? So sort of an oscillatory motion. Now this is the u, right? The amplitude in the sense.